All right, you got the notes for section 10.5, which deals with statistical literacy. So just some reminders about correlation. So this fig graph below shows a positive association between the y variable and the x variable, as higher y values are generally associated with higher x values. Because the correlation coefficient r is positive and close to 1, it's appropriate to say there's a strong positive correlation. So the closer r is to positive 1, the closer it lies on an exact straight line. Down below, you have a negative association as one variable increases, in this case x, the y values decrease. Since the points are quite scattered, it's not close to -1, it's probably say moderately weak negative correlation. So if your correlation is +1, they both increase, and if it's exactly 1, they all lie on a line. -1 would be line on a line decreasing. 0 would be essentially no correlation at all. Okay, so correlation correctness. So be sure both variables are quantitative. So you need numbers. Association with correlation. Association is a much broader term, whereas correlation should be used only for quantitative data to measure the strength of an association that we believe to be linear. Correlation does not imply causation. If the points line up nicely, it is tempting to conclude that variable y is reacting to variable x. It might actually be the other way around, or both variables might be reacting to a third variable. So just because it looks like one thing is causing an increase in the other does not necessarily mean it's true. And then be sure the underlying pattern of the scatter plot is linear. Strength of correlation is not an appropriate measure for data exhibiting nonlinear behavior. So if your data is exponential or something like that. Okay, example 1, tell whether each correlation is being used correctly, identify statistical areas. All right. The graph of per capita domestic product y against literacy rate x for 17 world countries is shown to the right. The strong positive association with r is 0.788, proves that raising a country's literacy rate will improve its per capita gross domestic product. So are we using correlation correctly? So in this case, not necessarily, because we're applying, so we'll say no. First of all, linear might not be the best, because these are relatively flat and then it climbs relatively sharply, so that an exponential function might be better. So linear may not be appropriate. And causation is questionable. We don't know that literacy causes per capita growth income. All right, research company reported a strong correlation between the religious affiliation of American adults and the types of charitable associations they support. Once again, no, because this data is categorical, not quantitative. We're talking about types, names of things. A famous study of college freshmen once showed that the high school measure that had the highest positive correlation with freshman GPA in college was the number of mathematics courses taken in high school. It showed the best preparation for college was to take lots of math courses. Let's see here. So once again, our issue is causation. Taking a lot of math courses will not cause you to do better in college. They're probably both responding to some other third thing, like the amount of time spent studying or something like that. All right, and the last one, a researcher in 1990 measured the heights and annual salaries of every person named Michael Jordan in Chicago. The correlation was astounding 0.97, suggesting a strong linear relation between the height and the salary amongst the group. Let's see here. The issue here is that you have one Michael Jordan in 1990 that has a very large thing. So like your scatter plot has a bunch of people down here and then one person way up here. So it's really easy to make a line look pretty good when all of your low points are clustered together. So once again, not really due to an outlier. Okay, so let's look here. The importance of randomness. So inferential statistics uses collected observations to draw conclusions about broader populations and real-world phenomenon. So example 2, which of the following sampling strategies would result in random samples from the population under consideration? That should be a question mark, not a slash. Okay. Your school wants to pick 5 random seniors to represent the school on a district panel. The names of the seniors are written on slips of paper and placed in a bucket. After the class president shakes the bucket, the blindfolded principal draws 5 names. let's see here. This one is actually not really, because the shaking doesn't really randomize. It doesn't mix it enough. So the people on the top are more likely to be drawn, or people who put their name in last are more likely to be drawn first. Okay, a group studying the increasing problem of obesity in America wants to estimate the percent of American teenagers who order hash browns with their breakfast sandwiches at a particular national fast food chain. They visit each of the chain's restaurants in Idaho and gather data from the first 10 teenagers they see ordering breakfast sandwiches in each restaurant. So this, once again, is not random. So there's no guarantee that one state may not be representative of the whole. Okay, Miss America contest wants to choose 8 state representatives at random for a publicity shoot. Each of the 52 women is given a card from a well-shuffled deck of 52 playing cards. The publicity chair then chooses 8 cards at random from another well-shuffled deck, and the women with the matching cards go to the shoot. This one actually is random. So you have randomized essentially in 2 places. You have 2 well-shuffled decks. They're dealt out randomly, so there's no way to fix the results. All right, samples, surveys, and observational studies. So we have some forms of bias. So you have undercoverage bias, occurs when some members of the population are inadequately represented. Voluntary response bias occurs when the sample members are self-selecting, and response bias occurs when the study design influences the results. So that could be like wording of a question, things like that. So let's see here. Local talk show host wants to, for a form of sampling bias, point out the problem. Okay. Local talk show host wants to assess the opinion of city residents on a proposed tax increase for public education. So he invites listeners to phone their opinions. According to his poll, 93%. So this is an example of voluntary response bias. You have more likely people who feel strongly will call in. Also, undercoverage bias, because you're only looking at his listeners. Okay, parent group opposed to proposed renovation of their high school auditorium passes a questionnaire at the football games. This question: should the school jeopardize vital school programs by diverting funds to improve an auditorium that is needed only a few times a year? So this is a response bias for sure, because the way that question is worded implies that it is a bad thing to do. Also, once again, you have undercoverage because you are passing this out to football games, so not the entire student or parent population. All right, seeking feedback on a new toothpaste flavor. Company supplied 500 dentists with free samples to give to their clients. With each sample came a stamped postcard asking the used to check 1 or 2 boxes, like the new flavor or don't like the new flavor. The company received 887 postcards back, 85% of which reported that the user, that should be the user. There we go. So let's see here. So this one, let's see, problem here would be like response bias, because you got some free toothpaste, so you may be more likely to give a higher thing. You have an undercoverage bias because your samples may be small. Okay, well, actually probably not undercoverage with 500 dentists, so we'll just go with response. Okay, biologist wants to gather evidence that nuclear power plants cause genetic defects in frogs that fed in nearby ponds. He sampled 50 frogs from the pond near his local nuclear power plant, discovered that 8% of them had genetic defects. This was, in fact, considerably higher than the rate in the general frog population, so we consider this to be good evidence supporting his assertion. Let's see here. So, call this undercoverage because he only selected from 1 pond near his power plant. Could have been different results near different power plants. All right, experimental design. So in an experiment, researchers impose treatments on subjects who are often volunteers. Each treatment is based on factors that might affect the response variable under a study. So, treatment would be, testing a vaccine. Your subjects would be, people who you're giving the vaccine to. The factors you're controlling for are looking at, be age, race, gender, things like that, how that may affect what you're trying to study. So in 4 important principles of experimental design: control, variation between subject groups receiving different treatments should be limited to the factor where you're purposely varying, and other conditions made as similar as possible. For example, if we were testing the effectiveness of a drug, everyone should get a pill, but only one group's pills should contain the drug. The fake pill is referred to as a placebo. The experiment should be blinded, meaning that neither group or anyone in contact with them should know which treatment they're getting until after the data are collected. So blinded means that the participants do not know whether they're getting the placebo or the drug. In some cases, you see a double-blinded, in which people are randomized, and then even the doctors don't know which person is getting placebo or drug. So the doctors are blinded and the participants are blinded. So randomization, subjects must be assigned randomly to the different treatments so that variation arising from uncontrolled factors will be randomly spread out among the groups. So if you're testing a vaccine, you don't want to have your group getting the vaccine be all males over than 30 and everyone else be in the other group. You want each group, both the control group and the testing group, to be as similar as possible with an even distribution that would match the total population. Replication, an effectiveness to observe multiple subjects, the more the better. To be statistically convincing, other researchers should be able to perform the same experiment on subjects from the same population with similar results. So, you want to make sure something is actually occurring. Blocking is a form of control. Pre-existing differences among the subjects that we might think might affect the response variable should be deliberately spread evenly but random among the treatment groups. For example, suppose there are 10 women and 40 men among the subjects of a 2-treatment experiment. It would be that men and women might respond differently to the treatments. We would randomly assign 5 women and 20 men to each group. If men and women did react differently, this would take the variable into account because they are evenly. If you overload one group with men or overload one group with women, you may get skewed results because the fact that they are male or female is having an effect on the results. Okay, so example 4, researcher wishes to test the effectiveness of vitamin C supplements for preventing flu. It's a diverse group of 200 men, women, and children who have volunteered for the study. Design an appropriate experiment that takes into account the likelihood that flu will affect different age groups differently. So essentially what you want to do is you have 2 randomized groups of 100. One group receives the placebo. Can't remember spell receives right. We're going to assume that's right. The other receives the treatment. And then compare. Since you randomize them, you're controlling for age and things like that. Okay, so example 5. Each of the following experiments suffer from at least one design flaw. Identify the flaw. In a study of multitasking, psychologists test the time it takes a group of volunteers to type the same 100-word text message, first listening to loud rock music, then listening to soft classical music, and finally listening to no music at all. So the issue here is the text is the same. So they should improve just because they're typing it more than once. By repetition, essentially. Okay, to test the effectiveness of an expensive online homework service, a teacher with 2 sections of freshman algebra assigns his 30 A period students for the service and teaches 30 B period students the same lessons but without the service. At the end of the year, he compares the grades. So you're not randomly assigned. So that's the issue here. So, maybe one class is opposite an elective or something like that, so the students are selecting into those sections based not on a random reason, or one's morning, one's afternoon, so you're more likely to pay attention to one versus the other. Okay, drug company tests new pain reliever on 100 arthritis patients whom it randomly splits into 2 groups. Half the patients given the new pill and the other half are told to continue their regular prescribed medications. After 60 days, the 2 groups are interviewed by representatives of the drug company to report their level of pain. So the issue here is the patients know which group they're in. So that may affect their outcome when they go to result. Well, I was on the same drug I was before. It doesn't really help because I'm used to it. Okay, so using randomness. Example 6, school is asked to choose 10 sixth graders at random to be part of a multi-year educational study. If there are 135 sixth graders in the school, how can they be chosen without bias? So let's see, you could number them. Then use a random number generator. To select 10 students. All right, 50 adults suffering from a certain medical condition have volunteered as subjects in an experiment to test the effectiveness of a new drug. Half will be treated with the drug, the other half will receive placebo. Explain how to randomly assign these 50 subjects to the two treatments. So, essentially you can do the same thing. So randomly assign numbers. And then random number generator chooses 25. So that's how you get your two groups. Okay, last thing we got here deals with simulations. So example 8, Fred is a 70% free throw shooter. How many shots will it typically take him to hit 7 consecutive free throws? So what we want to do is essentially we're going to random number generate again, assign. So 0 through 6 would be a made shot, and then 7, 8, and 9. So 7 through 9 would be a miss. So that's 7 digits out of the 10 digits. 7, 8, and 9. Yeah. And then just generate a list of numbers and count up how many times it takes him to get 7 consecutive shots. So the problem with this is it's, you'd have to run this test a lot of times. To get an idea. Okay. So example 9, the experiment, 64% of the 25 students showed improvement compared to only 40% of the 25 agree on the placebo. Could a difference as large as 24% arise by random chance? Or is that statistically significant evidence that the drug is indeed effective? Let's see here. Let's see. So 64% of 25 would be 16, and 40% of 25 is 10. So there's only 26 persons out of 50 showed improvement. Because this percentage doesn't matter, it actually matters the number of people here. So we can do a random test number generator thing. It actually ends up being not significant because this could occur by chance quite a few times. All right, that is the end of the section.